Okay, so for the last little while, we've been talking chemistry. Before I begin, I want to do a quick little recap of some of the skills we've worked on. Day one, we talked about what our stuff is. We give a better definition than stuff, though. We call it matter. And this is a question on your activity. What is matter? It's anything that has space and mass. If it takes up a volume and a mass, it's matter. And maybe the best way of describing what matter isn't is like to give a counter example, like say energy, light or heat. That's not matter, right? So, just gonna snag my keys back from him. Did you get it to work? Awesome, thanks, buddy. Okay, so we talked about categorizing our stuff too. Words like mixtures, colloids, suspensions, elements, compounds. We talked about that for a bit. We also then spent a day on safety. I want to reference an analogy I gave you guys a couple days ago where learning chemistry is like learning how to read. I talked with you about my daughters and reading, I believe. So just to kind of recap, Kinsey's in grade 6, and she is at the point where she can start to read full sentences. As long as the words are fairly small, she can read those ones. Whereas my daughter Cameron, she's 4, I'm working on teaching her letters, right? And like for her, success is like if she sees this letter right here, and she can tell me, Daddy, that's a P, that's great, right? Because sometimes she sees this letter right here, and she thinks that's a B, right? Like P's and B's and D's and Q's, they're hard for a 4-year-old, right? I think that's the gap we're trying to bridge today in terms of chemistry. My one daughter can read words. She can understand that this is the word pig, and she starts to mentally associate that with an object, and she knows that this is cat, and she can associate that. Whereas for Cammie, all she's able to do is just look at one letter at a time. This is what we're trying to jump through today. You have previously learned about our elements. Elements are like letters, right? One thing at a time. But now what we want to try to be able to do is put our elements together, and what do you call it when you put elements together? It's called a compound. So hence today and tomorrow's topics. Topic 5 is something called molecular compounds. Topic 6 is something called ionic compounds. We're going to basically be learning how to put our letters together into words. Does that make sense? And eventually, we need to be able to put our words into sentences. And we'll get to that in our last topic. And that's actually it for chemistry. Believe it or not, we are done in 3 topics. So 2 topics, we're going to talk about how to make our words in compounds. And then in the last topic, we're going to talk about how to make sentences, where it would look something like this. A plus B turns into C. And we're going to actually like write like chemical equations a little bit. But anyways, that's for next week. Is that a question hand or you're just stretching? Yeah, did you not use your periodic table on this? Oh, okay. Yeah, you guys can always have your periodic table. Yes. Yeah, always. I don't have it memorized. I have like a few things that I know, but like, you always get one. Okay. So I'm going to actually come back to this slide here a little bit later if I can. I know it's my first slide on the notes, but I'd like to loop back to this. Our goal over the next 2 classes is to learn how to name different words, basically, different compounds. Today we're going to talk about the molecular compounds. Tomorrow we're going to do the ionic compounds. But before I get there, I need to build a little bit more. So I'm going to start on this slide right here. How do you make a compound? Well, a compound means you take more than one element and shove them together. Classic example, H2O. I think you knew where I was going on that one. Right? H is hydrogen. On its own, this is like Cammie knowing a letter. O is oxygen. On its own, this is like knowing a letter. But we now need to know how to put those letters together and make a proper word. Now, again, think of my 4-year-old and how like a little kid is learning how to read for the first time. Sometimes my daughter, she thinks that like I've made a word. Like for example, she might go, Daddy, I've made a word here. I put a bunch of letters together. What word is this? And I have to kind of politely tell my 4-year-old, I'm sorry, Cammie, that's not actually a word. But isn't actually like a real thing, right? Because she doesn't get that concept as to like how to put a word together. Even my 6-year-old, she's only just learning. She comes home from grade 1, and she's like, Daddy, did you know that every word has a vowel? Right? Because you guys have heard this before, right? How you need vowels in words, right? And so like you immediately know that this can't be a word because there's no vowel in there. Okay. That's what I want to talk about today is how do we properly put the H's and the O's together to properly make this formula? Why is it H2O, not H7O? Why is H7O not right? In the same way that why is BG, BJH, why is that not a word? Before I get to that though, I need to talk about a concept called an allotrope. We're going to still focus on our elements for a bit. Okay. If you guys have your periodic tables nearby, can you grab those out? We need to write a little bit of stuff on it. So I'm going to flip back and forth between this slide and the previous one. Actually, no, I'm not going to. I can do it on this. You know how I just gave you the example of H2O and H7O? And I kind of suggested, like, why is H2O a word? Kind of like cat is a word. But why is H7O not a word? Kind of like why is CAAT? Like why does that count as a word, and why does that one not work? That's what I'm trying to get at here. To do that first, I need to explain what an allotrope is. Sometimes what we do with elements or compounds is after a symbol, see how we have this little number 2 right here? Maybe you've seen that before and wondered, like, well, what does it mean? Here's another classic example, CO2. You guys seen that one before, CO2? All right, the question might be, well, why is there a little 2 right here? Okay. What this refers to is how many of the very, very, very last element you have. So if you have H2O, it means you have 2 H's and a single O. That is like the combination ratio, which means if you have CO2, it means you have COO. And we're just kind of shortening it a bit. Here's another really classic example. It's this formula here, CH3CO2. What this means is that you have a carbon and then 3 hydrogens. Then you have another carbon and 2 oxygens. Right? And so it's these little numbers in the corner I want to focus on right now. Does that make sense, though? That number in the corner, it tells you how many of something you have. Okay. Now, the word we're going to use, though, is for elements, it's called an allotrope. And the example I want to give is imagine you're going to Costco and you need to buy something. Good old Costco. Imagine that you want to buy one of something. Well, sometimes, like when we write Na right here, this sodium right here, you're just buying one of it. Like you're going to Costco and you need to buy one jacket at Costco. You need to buy one of them. But you know how you can buy like a multi-pack? Like my wife just went to Costco the other day and bought like a package that had like 8 toothbrushes in it. Or, you know, like there's, you know what I'm saying here? Where you can have like a whole bunch of things at once. That's an allotrope. And there are some things that they only ever come in groups of 2 or 4 or 8. And so naturally on their own, in their elemental form, where they're not even forming a compound, you can't find them unless they're in a group. Like for example, mercury. Mercury always comes in groups of 2. You can't buy at the store of elements in Costco, you can't buy one mercury. You're always buying 2 of them. They always come in a 2-pack. And there's actually a lot of these that I want you to write down on your table. Find somewhere on your table and write these ones down. There's actually one missing on this list that I always forget, chlorine as well. Many of these elements right here, they only ever come in a 2-pack. So if you wanted to go to the store and buy one bromine, you can't. You have to buy like 2 of them. Okay. And there's some really cool ones actually. Sulfur only ever comes in 8s. Phosphorus and arsenic come in groups of 4. So if you could, somewhere on your table, can you write down all of these on the list? Because you're actually going to want to know these at some point. So Hg is mercury. Yeah, Hg is mercury. So what I'm trying to tell you here is that like when we write out mercury, from now on we're never going to write Hg. It's always going to be Hg2, meaning that it always comes with 2 together. It always comes in a 2-pack. And whenever you write P, if you're writing P by itself, you're going to write P4. Because it always comes in a group of 4. It's like you go to Costco and you want to buy toothbrushes, and Costco doesn't sell you one toothbrush. Right? If you're buying toothbrushes at Costco, you're buying like 4 of them, or 8, or 20, or something ridiculous, right? Does that analogy make sense? So we need to memorize just a few basic ones. While you're writing some down, I want to point out one that you're probably aware of. Has anyone ever heard of the ozone layer before? Heard of the ozone layer? That is O3. The ozone layer is when oxygen comes in a 3-pack. And so what O3 really means is that you have 1, 2, 3 oxygens, and like that is like all shoved together. Now, is this a compound, however? The answer is no. Even though there's 3 different things inside of this thing right here, it's not a compound because they're all oxygen. So it's still an element, but like it naturally comes in a group of 3. Now that's the ozone layer. But oxygen gas, this guy right here, it actually comes in groups of 2. And so oxygen gas that you breathe, which is the O2 variety, it comes with 2 O's in a grouping. Bromine comes in a group of 2. So if you ever want to buy bromine, you have to buy 2 of them. You can't buy just one. That makes sense. And I want to introduce this concept because it's this little bottom number right here that when we do compounds, we have to get right. We have to know how many like groupings there is. Okay. The analogy I want to move towards then is when we eventually talk about H2O, this is like a multi-pack. Okay. So like this is where you buy like 2 toothbrushes. This is where you buy 3 toothbrushes. You know what water is like? It's like where you buy a multi-pack and you get 2 things of toothbrushes and a thing of floss. Say that again. When you buy water, a compound, you get 2 H's and you get an O. Now there's 2 different things in this multi-pack. This multi-pack here, this multi-pack here, this multi-pack here. It's the same thing over and over again, right? But this one here, you're getting floss and a toothbrush. If I were to write out a different compound, like for example, C6H12O6, this multi-pack, you're getting 6 toothbrushes, 12 things of floss, and 6 little mouthwash samples. And all of this comes in one big pack. This is a compound because there is more than one thing there. Whereas all of these things that I've drawn here, they are still elements because there's only one thing. Is that clear? Okay. I want to actually talk about a really unique allotrope, carbon. I don't know if you guys know this, but there are many different forms of carbon. And those are the allotropes. You guys are using a pencil, right? Or maybe a pen, but say you're using a pencil. We call it lead. Like we say, oh, the lead broke in my pencil. But if you guys didn't know, we don't use lead anymore. We used to. Why are your pencils not lead anymore? Yeah, it's very toxic, yeah. So like if you are a person who chewed your pencil and it was made of lead, you would kill yourself. So we don't make pencils out of lead anymore. We actually use graphite. We just call it lead for some reason. Graphite is a form of carbon. Now, I don't remember which allotrope of carbon it is, but like for the sake of argument, I'm just going to call it C10. And so graphite is where carbon comes in a 10-pack. Here's what's really cool. Diamonds are also carbon. And I don't remember which allotrope it is, but like diamonds might be when carbon comes in like a 28-pack. Okay. The number that's going in this bottom corner here tells you how many of them come in a grouping. So there are 4 sides to any element. Okay. You guys remember this top number right here? That's its mass number. This bottom number right here is its like protons. This right here is like whatever its charge is. But if we put a number in this bottom corner right here, that tells you how many you're getting in a grouping. So if I give you like x3 in the bottom corner here, what that really means is that you have 3 x's. And this 10 right here means you have 10 carbons. So anyways, the point I wanted to make about carbon here is that there are many different forms of carbon. This is soot. Like say you burn something and it turns into ash, that's also carbon. And all of these different things are different forms of carbon. It just depends on which like grouping you have. So if you have the 28 grouping and it makes a diamond, that's really valuable. No one really cares about soot because that's like C1, I think. If it comes in ones, it's soot. Actually, let me talk about that for a second here. If it only ever comes in a group of 1, we don't write a number afterwards. Okay. So many things like, say, sodium comes in a group of 1. We don't write the number 1 afterwards. Or calcium comes in a group of 1. We don't write the number afterwards. Does that make sense? Okay. So what I want to get to now, though, is our compounds. Okay. So our compounds are going to be something like this. Okay. here's some typical compounds. What I need you guys to first be able to understand then is when we put our words together, those small little numbers, they tell you how many of something you have. For example, if I give you NaCl, it means you have 1 sodium and 1 chlorine, because I didn't write any little numbers afterwards. But if I give you this compound, CaCO3, well, Ca means you have 1 calcium. C means you have 1 carbon. But you guys see this little O3 right here? It means you have 3 oxygens. Yeah. So if you like my Costco analogy, this is buying a multi-pack. You went to Costco and you bought a multi-pack that had, I don't know, it had granola bars, and it has juice boxes, and it had fruit roll-ups. Right? And it came with 1 granola bar, 1 juice box, and 3 fruit roll-ups. That's what this multi-pack has. Right? And that's what makes it a compound. Okay. What we're going to focus on today and tomorrow is, how do I know how to put it together properly? How do I know that with Ca1, C1, and O3, rather than being Ca7, C42, O3? Does that make sense? Like, we have to talk about why these numbers are what they are. Right? In the same way that when Cammie's learning how to read, she wants to know why that's not a word. Because she's like, well, those are all letters. Why is that not a word, Daddy? Does that analogy make sense? Now, here's the thing. Every compound has a chemical formula, and it has name. And that's what we're going to work on, is making sure that we know the formula and the name, and that we can put those together properly. You guys already know a couple of formulas and names. I'm almost sure of it. Let me give you a couple that you already know. For example, this one right here. As soon as you see that formula, you probably know what its name is. This is water. Right? And this one right here, CO2. Carbon dioxide, yeah. That's my goal today. That's one of my goals today, is to be able to talk about, like, well, when you see these things together, what do you verbally call it? You know, just like when Cammie's learning to read and she sees these together, she knows that CAT is a cat. I mean, I can't even, like, write that there, but, like, you know what to say. Here's one more that maybe you're aware of. NaCl. This is called sodium chloride. Maybe you've heard of this one before. Anybody know what sodium chloride is? It's salt, yeah. Yeah, it's just common table salt that you'd use to make your, I don't know, corn on the cob taste really good. Why did we put salt on? So before I keep going, I got some more pictures I want to show you, just to make sure that we're all clear on the concept here. This one here is salt, NaCl. NaCl, if I don't write a little number in the corner here, it implies that there is 1. Okay. So 1 sodium, 1 chlorine, there's your compound. Okay. Whereas this is water, H2O. Is it clear to everybody that you need to have 2 hydrogens? The 2 applies to whatever comes right before it. And this oxygen, it really implies there's just 1 of them. Can I go back a slide? I just want to refresh on this one right here. This CaCO3, Ca there's 1 of, C there's 1 of. This 3 then applies only to what's in front of it. I want to show you a different example. We're not ready to do this a lot yet, but I should show you now. Let's say I give you this compound here, NO3 in brackets 2 with a Ca. We're going to get to something like this eventually, so I figure I might as well show you this one now. This one here is even like doubly confusing. Let me tell you what the answer is for this one here, and then maybe we'll work backwards. This has 1 calcium, this has 2 nitrogens, and this has 6 oxygens. Let me explain why now. See how this thing right here is in brackets? And there's a little 2 afterwards? Well, that 2 means that there's 2 of whatever's in brackets. So if I really wanted to write it, I could write it as calcium, and then I could write it as NO3, and a second NO3. See how there's 2 of them there? Well, now add it up. How many calciums do I have? 1. How many nitrogens do I have? 2. Now this 3 applies to that oxygen. This 3 applies to that oxygen. What's 3 plus 3? 6. If you could follow that, that's absolutely fantastic. We're not doing that yet, but that's where we're going to go eventually. Okay. So I think I've made my point. Hopefully I've made my point here, is that I need you guys to know how these little numbers down here in the bottom corner, how they work. Okay, so now I'm ready to start teaching you how to name compounds. I've got a flow chart here that I'm going to use to try to like break things up into pieces, because naming compounds can be quite confusing. Today, we are going to focus on things that are called the covalent or molecular compounds. This will be what we do today. And then tomorrow, we will focus on these ones here. So we're just going to do this into like in pieces, if that makes sense. So today we're going to keep things simple. We're only going to talk about how to name something that is considered a molecular compound. Okay. So let's talk about molecular compounds. Or we use the word covalent. Okay. I want to start by giving you an analogy. Imagine that you need to go to the cafeteria downstairs and you want to buy some food. And the item that you want to buy costs, let's say, $6. Say it costs $6. And person A has $4. And person B has $2. Are either of these two people actually able to buy the item on their own? No. But if they share their money and pool their resources, they can eventually get to like $6. They're going to share their resources. That's actually how covalent bonds formed. Is what ends up happening is elements will share electrons with each other. And by sharing their electrons, they form a bond. I'm going to fast forward in my notes if I could to try to find a picture example. No, I'm going to draw one actually. I'm going to give you an example here. Let's do water actually. Yeah, let's do water. You guys remember doing Bohr diagrams? Where we would do like these rings that kind of go around there? Okay. Let's do water. What's the formula for water? H2O. Okay. So we need two H's, we need an O. I'm going to draw the oxygen first. Oxygen is number 8. So if I start drawing its electrons, it needs 2 electrons in the first level, and then it's full. That first level's full. And then the second level, there's 1, 2, 3, 4, 5, 6. How many electrons were capable of fitting in that next level, though? 8. So it's like there's 2 open spots. There's like an open spot, let's say right here. And why don't I say there's an open spot right here? Does that make sense? Now let's talk about hydrogen. Hydrogen, if I were to draw a single hydrogen, hydrogen just has just 1 electron, right? And well, why is it H2O? Well, because that 1 electron can kind of get shared into this spot right here. But why is it H2O? Why do we need 2 hydrogens? Because the other hydrogen has 1 electron, and it gets shared into that spot right there. Does that help explain why we have H2O and not H7O? Remember how I started class by saying why it's that? That kind of explains the rationale, is that we're going to share these electrons, and they're going to merge together and fill in those open gaps right there. That's how these compounds form. So let me talk to you about how to name these things. There are some rules we need to memorize. The rules are fairly straightforward. How we do this is we need to have a prefix, then you write the first element. Then there's a prefix, there's the second element, and you change the ending to "ide." That sounds really confusing. It's not, because you already know how to do this. Here's a compound, CO2. You guys know what to name this, right? What's the first thing here? Okay. Now, whenever there's just one of something, we don't need a prefix. So, although we would want to have a prefix, there's one of it, so we're going to ignore that. Then I'm going to write my first element. Now, what's O stand for? Okay, so I'm going to make oxygen, only we change the ending to "ide." So rather than writing oxygen, we write it as oxide. But before we do that, we needed a prefix. Well, the prefix is based on this number right here. How many oxygens did we have? That's where di came from. Di is the prefix for 2. Now, you might even know some of these prefixes, because I've got a slide here on them. Di is 2, but you guys know some of these, right? Like tri, like tricycle, 3. Tetra is for 4. Penta, like pentagon, is 5. Hexa, 6. Hepta, 7. Right? What I would suggest is at some point, write these down somewhere in case you don't have them memorized. You will memorize them at some point, But the way it basically works is if I give you a compound, like I'm just going to make a random one up now. I'm going to go with P7O2. Hypothetically, let's say that's actually like a word. This isn't my daughter putting random stuff together, but let's pretend that actually was a compound. Here's how we would name it. 7 means we would need hepta. Then we'd say what it is, phosphorus. Right, so that gets me started. 7, hepta, phosphorus, O2, dioxide. Oops. That's how you'd name this. So you always kind of name it in reverse. The number that's down here tells you whether it's a di, a tri, or a tetra, whatever word you use there. And then after you use that, then you tell me what it is. So that now explains to you why it's called carbon dioxide. Carbon dioxide. That makes sense? Great question. Okay, so we often skip mono on the first thing, but has anybody ever heard of carbon monoxide? Okay, so carbon monoxide would be CO, because if we just say carbon by itself for the first one, that implies 1. And then when I said monoxide, that implied there was just 1 oxygen here. So carbon monoxide would be CO. Yeah, if you ever have something mono something, it would be 1 of each. So let's try some examples, because I think maybe this is starting to click a little bit. Okay. Here's some classic examples of things that we've maybe seen or haven't seen before. Right? The first one you've already seen, carbon dioxide, Here, let me use the laser pointer. Here we go. CO2, right? We call it carbon dioxide. So what would you call this? This would be called a di-nitrogen monoxide. See how I had to use the word mon here to imply that there was just the 1 oxygen right here? Right? So we only ever use mono if the second thing there's 1 of. This would be a di-nitrogen trioxide. Yeah. Good question. I've got a slide on that, but why don't I do that now? Can you guys fast forward right to the very end? I have that question predicted, but let's go to the slide right here. There are many compounds that have been given like a formal name. Water's true name is actually this. It should actually be dihydrogen monoxide. That is actually what water's name should be. But there are a lot of compounds that like, we give it like a nickname, right? Any of you guys have like a long name and like you have a nickname? Like my full name is Christopher, but people call me Chris, right? In the similar sort of way, H2O is dihydrogen monoxide. That's like really a mouthful to say every single time you talk about water. So there's a few things that we just give a shorter name to, if that makes sense. So some of them you just need to memorize. So that's why I have a slide here that talks about a few maybe you've heard of, like methane. Methane is CH4. This would be a carbon. Nope. It is a tetra, because there's 4 of them. And then hydrogen would turn into hydride. But rather than calling it carbon tetrahydride, we just call it methane. It's what we use to like heat our houses and stuff. Does that answer your question, by the way? Hey, welcome. Brock, did that answer your question? As to like why we call it water? No, he's not hearing me. Brock, did that answer your question? Okay, cool. Okay, let me go back to where I was here then. So you guys can probably follow along on this a little bit here. We've got like 5 and 1, so we call this phosphorus pentafluoride. Carbon tetrachloride, di-nitrogen trioxide. Right? Once you figure this out, it's actually kind of a cool little pattern. Right? So let's try practicing naming a few. Yeah, Jacob, go back. Yeah, for sure. This one right here. Yeah, so it's always backwards, right? Like you write the word nitrogen, but then before the nitrogen, you have to tell me how many there are. So since there were 2 nitrogens, we got to go 2 nitrogens, 3 oxygens. You're always kind of going like a backwards pattern. Okay, let's try some examples then as a group. So what do we call CO2? C is carbon. You guys already know this one, right? This is carbon. Since there's only 1 of them, we don't need to write the mono for the first word. And then for oxygen, you'd change it to oxide. And since there's 2 of them, we call it a dioxide. There you go. Or for the next one right here, this is a different grouping of it. Just like, remember how you could have oxygen in a 2-pack or a 3-pack? Well, here, there's only one of them. So this is now a single carbon, and it is a monoxide, because mono is for the one of them. Okay, don't yell it out. Try the third one by yourself and see if you can figure out how to name this third one here without me telling you or without yelling it out. Try it yourself. What would we call an N3H6? So hopefully you're this far. Nitrogen is N. But you need 3. 3 is a tri. So the first bit would be called a trinitrogen. Yeah, hydrogen's a weird one. Hydrogen changes to hydride. Hydride, because we always ended in "ide. And it would be called a hexa, because there's 6 is what hexa is. So this is called a trinitrogen hexahydride. Nice. Those were like, that was a really bad high five there. Okay, let's try the next ones here, guys. What if I go the other way? What if I give you crazy intense words like this? How do we work the other way around? So let's try this. Silicon. Stay with me, guys. I need 10 more minutes, okay? I will probably go right to the bell. Sorry. That's because I started class with some work time. Silicon is the letters Si. How many silicons do I need? Just one, because I didn't give a thing in front of it, right? Then it's tetrafluoride. Now, don't put the 4 right here. Some kids do this. They go silicon, tetra, fluoride. That is wrong, what I just did there. Because the way we interpret it is that we needed 1 silicon, and then fluorine, we needed 4 of. That's how you'd write it. Or tetraphosphorus. That would be P for phosphorus. Tetra means 4 of them. Then it wants a decaoxide. Oxide is oxygen. 10. Or dinitrogen. So nitrogen with 2. Monoxide. Just write a single O. And you guys now know how to read some words. Now, is this all of the words in the English language? No. Okay, stay with me, guys. I do need to keep going, okay? So don't get too distracted here. But just like my daughter who's learning how to read, okay, I've shown you guys how to read some really simple words, okay? There is more than this. On this flowchart I had back here, we're gonna cover a couple of branches of ionic compounds tomorrow, and it's gonna get a lot more tricky, but for right now, this is how you name covalent molecular stuff. I gotta point out a couple things though, okay? In order for it to be covalent or molecular, this is the very, very, very first slide, and I skipped the first slide. I wanna come back to it now. Molecular or covalent compounds are only between 2 nonmetals. There are very, very, very specific rules for this. You can only use things, you know how you have your periodic table? It looks kind of like this. Here's your table. Kind of has like this sort of look to it here with the row below. Remember how there's the staircase line over here? This naming scheme only works if they are nonmetals. Both of the compounds. You guys might have noticed that every single thing I used, with the exception of hydrogen, hydrogen is up here. It's actually an exception. Hydrogen is actually considered a nonmetal as well. Guys, stay with me. It has to be nonmetals. Okay? And this is really similar to when I teach my daughter how to read. I don't teach her like silent letters. She doesn't know that PH makes the sound F yet, right? So we're biting it off in little chunks. But we're only ever looking in the nonmetal section. Okay, a few more things, then we gotta go. I've got 10 minutes left, so try to stay with me here. We need to talk about some word association. The example I gave earlier was my daughter Kinsey learning CAT says cat. And it is nice that she knows that it's CAT for cat, but she also has to, in her mind, be able to understand, well, what is a cat? She has to know, okay, well, it's a furry little creature with 4 legs that has hair that drinks milk. You also need to know properties of what we're talking about. You get what I'm saying here? Like, I need you to have like a mental association. It is great that you can tell me that this is this, and this is this, and this is this. But like, do you know anything about what dinitrogen monoxide looks like, or tastes like, or feels like? we also need to talk about that as well. So my next few slides are some generic properties of these molecular compounds. Okay, let's talk about a few of them. They have very low melting points. Okay. What does a melting point mean? If something's melting, what state of matter is it? If something is melting, what state of matter is it? If something is melting, what state of matter? There we go, liquid. Does that make sense? If something is melting, it means it's a liquid. Okay. I want to give you guys a really good example here. A classic molecular compound is water. And what state of matter is water probably going to be? A liquid. Right? Now, I mean, if we make it really cold out, can we make it a solid? Sure, if we make it cold enough. Okay. Not only that, but maybe it's even a gas. Because here's another classic example, CO2. Carbon dioxide is a gas. So what I mean by the low melting point is that most of the compounds that we wrote right here, if I gave you a state of matter, they are probably either liquid or gas. Okay. Like nitrogen monoxide, I believe this is laughing gas. Okay. You guys heard of that before, laughing gas? So yeah, it will wear off eventually. Now, I could be wrong. One of the nitrogen oxides is laughing gas. I forget which one. Okay. But like these things are usually liquids or gases. Okay. Here's another property I want you guys to know. If they do become a solid, their crystals are very weak. Again, let's think of water. Can water become a solid? Yes. For example, in the last couple of days, anybody see like your parents or you have to like scrape your car windshield off in the morning with ice like frost on it? Is it hard to get the frost off the windshield though? I mean, okay, it's a pain in the butt, but like a scraper will remove it. Why? Well, because water's crystals are very weak, like a snowflake. Does that make sense? Whereas if you had to take a scraper to this table, I don't think you'd be able to scrape the table all as well, but you can definitely scrape the ice off. Okay? So there's another property I want you to know. I've got a chart here that talks about some melting and boiling points. It is highly likely that you will get a PAT question where they're going to give you some properties and they're going to give you compounds that have like high or low boiling points. If it has a low boiling point, that probably means that it is molecular or covalent. Later, we're going to talk about things that have high boiling points. That'll be tomorrow. Those things will be ionic. But we can actually generally tell what type of bond it has based on its boiling point, or sorry, I should say melting point actually. Melting point is what we talked about today. Okay, here's another property. These things do not conduct electricity. Now, I don't know that I can fully explain this until I talk about things that do conduct electricity, but here's the basic concept is that in these things as pure form, if you try to run electrical current through it, it shouldn't occur. And the last couple slides I've got here, because I know I need to wrap up here, I want to illustrate what we're going to get to tomorrow. Okay. Today we talked about covalent bonds. And covalent bonds are where there's going to be some shared electrons. Remember when we talked about like H2O? And they're going to merge their electrons to each other? That's what this picture right here tries to illustrate. Give me 2 more minutes, okay? I'm almost done. This is where a nonmetal. Give me 2 more minutes. Don't pack up just yet. Don't pack up. And a second nonmetal. When these two nonmetals merge their electrons, that's a covalent bond. Tomorrow, though, we're going to talk about an ionic bond. Okay? And these things work a little bit differently. This is where you have a metal and a nonmetal. And that's going to be like part 2 of my lesson. Okay? So let me do a quick summary because I think I've covered all my slides here. We have 2 lessons back to back that we're doing. The first lesson we covered today, we kind of bit off a little bit in terms of how to name things. When we name these things, though, it has to between the nonmetals. They have to be on that side of the staircase line. And they're really easy to name. All you use is you use like dioxides and tetraphosphoruses and stuff like that. Okay? You guys have any questions? All right, you guys are kind of packing up on me, so I guess we're wrapping up. Okay, one last thought here, and then we're just about ready to go. I noticed a lot of you finished up some progress logs. Thank you for that. If you want to redo stuff, you're more than welcome to. But like sooner than later, we need to move on past the genetics unit. We need to move into new stuff. So, You guys are still hearing me, okay? So that being said, I need you guys to start working on that first assignment, okay? If you haven't finished that first assignment or getting close to it, that should be like number 1 on your to-do list, okay? Because there's 2 assignments this unit. I don't want to give you a due date yet if I can avoid it, but can you guys start working on that assignment? That makes sense? Okay. You guys can, I guess, pack up and take off any second here. The bell's going to go. If I didn't get to you today, by the way, I'm like this right here, come find me again, right?